everybody, and greetings from Costa Rica and from the Simposio Latinoamericano Logica Matematica. Everybody here says hello, and greetings to Kobe and Sergey. I'm sorry I can't be there with you. On the other hand, as I hear about heat waves, chaos at Heathrow, rail strikes, I'm kind of happy that I'm not there. I hope the conference is going well and you're all having a good time. So let me begin by saying I would like to dedicate my talk to Derek Goldray. Derek is died earlier this month, and his funeral is actually today in Oxford. And people who were, anybody who passed through Oxford in over many years will have encountered Derek. He was one of the first people to do the math and philosophy degree when it was first introduced. And he started a PhD with Robin Gandy, but never actually wrote up his thesis because he got much more interested in teaching. He worked at the Open University for all of his career, but he also kept his hand in by teaching students at Oxford. And he was a really great teacher, a really great person. He was very kind, very generous, and he was always very warm and welcoming to me, and really made my visits to Oxford a real pleasure. So I'm very sorry to say goodbye to Derek. But on a more cheerful note, we are here celebrating the work of our friends Kobe Petersil and Sergey Starchenko. And so I want to tell you about a project that I've been working on with Pablo Cubides Kovacic, in which we're very much inspired by the work of Kobe and Sergey on the idea of developing complex analysis on a non-standard algebraically closed field by identifying it with R cross R, where R is an O-minimal expansion of a real closed field. So looking at this, Paulo and I were thinking about, well, could we do a similar thing for the complex of the kind of quote complex analysis of a algebraically closed valued field? Now, I have to say that this project has been somewhat put on hold by the pandemic and by being deputy director at the Fields Institute. But we haven't really taken it past the very first step. But the very first step is to think about what are the functions that we would be looking at, and what kind of minimality conditions are available to you in order to even start on the project. Because of course, the point of Kobe and Sergey's work is that you use the fact that you have an O-minimal expansion of the real closed field. So you're looking at the functions are definable functions in an O-minimal expansion. And you use the properties of O-minimality to know the behavior of the definable functions in ways which, when you're working on a non-standard model, you don't have the classical behavior of your analytic functions. So the analogy for a real closed valued field, if you have a valuation, of course, you're not going to get O-minimality, but maybe you can get something which is an approximation. So of course, what we would hope to get is weak O-minimality, and then hope, well, this is the bit that's just a very vague idea of where we might want to go, is that weak O-minimality would give us enough properties of the definable functions that we can then try to develop the complex analysis. So that's the very long-term goal of the project. And what I want to tell you about today is just what the particular expansions that we want to look at, what functions we want to add to our structure, and then the fact that we do get a weak O-minimality result. Okay, so we have to choose what functions to look at. Right. So I'm also going to be doing this is what this will be a review of some of the development of the theory of adding analytic functions to a field. and kind of what sort of things what results have been done over the last 20 or 30 years, and then where this result fits into that context. So Peterson and Starchenko work with real analytic functions definable in an O-minimal expansion of a real closed ordered field. And the way that you set this up is, so we take the ring of power series with coefficients over the real numbers, where X is a multivariable. And we'll write calligraphic A for sets of various subsets of the collection of power series that we want to look at. So in the first instance, we'll look at the power series that converge on an open neighborhood of the unit box, -1, 1 to the n. And then for every power series, for every formal object, we define the function f hat, which is given by the value of the series at the element, provided that the element is in the unit box -1, 1 to the n, and then 0 outside of it. And it's a kind of important as part of this that we're looking at this closed and compact set, which is the interval -1, 1 to the n. And then we're making sure that our power series converge on an open neighborhood of that compact set. And that's part of what makes all this work, is that we kind of have control of on the level of convergence on that box, because the power series converge not just on the box, but on a neighborhood of the box. But then we just cut them off. Okay, so then we look at take the language of ordered fields, add symbols, function symbols for all of these functions that we're interested in, and then assume that the function symbols are interpreted in the standard model by the functions f hat, the restricted analytic functions. And then the theorem which makes all this get started is that the theory of the reals in this language is model complete and O minimal. Okay, that's not exactly the way Denef and van den Dries expressed it in 1988, but and maybe I'm lying to you a little bit about exactly what language they're working in, but that's kind of the moral of morally what they were saying. Now, if we look at a non-standard model of R in this language, I mean, after all, we have this theory, then part of what we can do is to look at all models of the theory and not just the one that we originally thought of. A non-standard model will naturally come with evaluation, where the valuation ring is the finite elements. So if we use the usual trick of adding a binary relation symbol for the valuation and call it div, and then add that to the language, then what we get is an ordered valued field in which we have function symbols for these restricted analytic functions, which are convergent in the sense of the ordering. And the associated theory is weakly O-minimal. This is called an example of a T-convex theory in the sense of van den Dries and Muhlenberg. So that's a nice situation. We have this weak O-minimality, but it's not it's not the functions that I want to look at. For one thing, these are the functions. These are the ones that Kobe and Sergey looked at already. And this is the situation, although they weren't looking at it in the language with evaluation. But I think if we're trying to do complex analysis on a valued field, we should be looking at functions which are convergent in the sense of the valuation, and not functions which are convergent in the sense of the ordering. So we should want to look at a different collection of functions. Just for my notation, I have a field with evaluation, which is a function from the field to an ordered abelian group written additively. It's a homomorphism from the multiplicative structure of the field to the additive structure of the group. It has this superadditivity, or maybe subadditivity, superadditivity, I think I should call it. Valuation of x plus y is greater than or equal to the minimum of the valuation of x and the valuation of y. And that detail, of course, is important when we're trying to look at convergence of power series. If my field has an ordering, then I will say that it's convexly valued if the evaluation respects the ordering in the sense that if let's see, I can write this into here we go. If I have x less than y, and they're both positive, then the valuation of x is greater than or equal to the valuation of y. And we have the additional structure, which I'll write in Leonard-Lipschitz notation. K0 is the valuation ring, K0 is the valuation ring, K00 is its maximal ideal, and I'll write K tilde for the residue field. And if the valuation is convex, then K0 and K00 are both convex sets. So that is, if I take X and Y, which lie in the valuation ring, take Z, which lies between them, then Z also has to lie in the valuation ring. And then in this situation, the ordering will induce an ordering on the residue field. Then for this nice setup, Cherlin and Dickman proved that if I take the theory of a convexly valued real closed ordered field in the language in which I have both an ordering and a symbol for the valuation, then we have quantifier elimination. So we've got a good algebraic theory to work with. Now, using the valuation, we also get a topology where the basis of open sets is given by the balls, which we write so the set of X for which a closed ball, center A, radius alpha, is those X's which are distance alpha from A in the sense of the valuation, or then an open ball, but they'll both be both closed and open in the topology. So with this notation, I have the valuation ring is itself the closed ball center 0, radius 0, and we just have to get used to the idea of having radius 0 for our balls. And the maximal ideal is the open ball center 0, radius 0. So what does that mean for convergence of our power series? If I assume that K is a complete valued field, then a power series will converge in the valuation topology, well, in the usual way, provided the sequence of partial sums is a Cauchy sequence, but this is in the sense of the valuation. So then that says that if I take two partial sums, if I choose any level of gamma in the value group and take partial sums, then I should be able to go far enough out so that the valuation of their difference is greater than gamma, so getting close to 0. Well, since the valuation of their difference, I mean, since the difference is the sum, of course, from n plus 1 up to m, or maybe m plus 1 up to n, of the summands fi x to the I, and because the valuation of a finite sum is greater than or equal to the minimum of the valuation of the summands, then I just have to look at this, the minimum of the valuation of the summand. So in order to get that this is sufficiently large, I just need to know that each individual term, the valuation of fi plus I times the value of x, goes to infinity as I goes to infinity. So we have a apparently much weaker condition for convergence on our infinite series here. So what does that mean? If I want to get convergence on the maximal ideal, well, I just have to have that if my value of x is strictly greater than 0, then of course the I times the value of x is going to go to infinity automatically all by itself. So I just have to make sure that the valuation of fi don't interrupt. So they just have to be bounded below. If I want to get convergence on the valuation ring, so on a slightly larger set, then it's I don't get the valuation of I times the value of x going to infinity anymore. So I have to make sure that the coefficients take me to infinity. So that has to be, those coefficients have to go to infinity in valuation. And if I want to get a convergence on a slightly larger ball, so a ball here, to think of epsilon as being negative. So if I want convergence on a ball which strictly contains the valuation ring, then I just have to know that the valuation of the coefficients are sufficiently larger than I times epsilon in order to get that convergence. So we call these the overconvergent series. So with the analogy with the reals, then in case of the reals, we looked at a power series which were convergent on the compact set, the interval -1, 1 to the n. And in the valued field case, we think of the valuation ring as being the appropriate analog to that unit box. So if we might want to consider power series which converge on the valuation ring. And so we just need this weak condition, or well, medium condition on the coefficients. We might also want to consider, in order to get more control over the convergence or the rate of convergence, we might want to look at the overconvergent series. But we kind of have an awareness that it's easier to get convergence if we're looking just on the maximal ideal. And these are the kind of considerations that you keep in mind as you're trying to work out which series you should look at, and to see how much you can control their behavior. So Leonard Lipschitz looked at this particular situation. So taking convergent power series on a complete algebraically closed valued field to see what kind of model theoretic results you can get. So this is in the context. This is 1993. This is relatively shortly after the Denef-Van den Dries proof of quantifier elimination for a real closed field with the restricted analytic functions, and then also for a p-adically closed field with the restricted analytic functions, where in the p-adics you take the functions which converge on the valuation ring. And so the question was around, well, so what happens if you look on an algebraically closed field, and what can you say? And here it gets harder because the valuation ring is no longer compact when you're looking at an algebraically closed field. So what Leonard Lipschitz had to do was to add function symbols for these functions given by power series, in which he looked at the variables in two sorts. So he separated the variables and gave what are called separated power series. And we looked at the variables which range over the valuation ring, and then variables which range over the maximal ideal. And as we saw, if your variables are ranging over the maximal ideal, then it's easier to get convergence. You don't have less strong of a condition on the coefficients in order to get convergence. And so you have, that's kind of, you can allow a bigger range of a bigger collection of functions. Whereas the variables which are on the valuation ring, you need a stronger condition on the coefficients in order to get convergence. So Leonard wrote down a very particular collection. I'm being a bit vague here when I say a particular collection A, because it's quite a technical definition. So the point I just want to make is that you can write down you can decide what the collection of power series is that you're going to look at, and then put them into the language on your algebraically closed valued field, and then you will get a theory which is model complete. So again, you get something reasonably nice, provided you've made a very careful choice of the choice of functions. So then in the early 2000s, Ralph Kluckers and Leonard Lipschitz said, well, can we articulate what is the kind of axiomatically, what are the properties of these, what are the properties that we need of our family of functions in order to be able to run the proof of quantifier elimination? Because all of these proofs, they're basically doing, they're all doing the same thing. And so their idea was, well, okay, let's just write it down axiomatically. So in the paper, which deals with analytic structure, which is really kind of the final word on this whole thing, it's from my point of view, a very, very beautiful paper. They said, all right, let's define this idea of a separated analytic structure in very general terms. So we take a ring, which is, that's a Roman A, a collection of subrings of the rings of formal power series, in which we work in two sets of variables. We take the X variables and the row variables. And so I've just, in a very formal way, I've got a bunch of variables. I can take formal power series in all of those variables, and then I choose a subring of the set of all those power series, and I call that A. And then I just make it a family by having I have M X variables and N row variables. And the first thing is that we make sure that it's big enough. We put in all of the polynomials. So that's a start. And then I said here satisfies natural compatibility conditions. If you want to write that down, it's very, very technical, but basically it just says that if you take a polynomial and M plus 1 variables, but it doesn't actually involve the last variable, and that's in your family of, in your subring, well, then when you just cut out that last variable, then it should be in the subring below, and statements like that. So all those things which say, look, all this collection of power series that I've chosen fits together in a reasonable way. It's a nice family. But then what you want to do is you want to make sure that you have Weierstrass preparation, because that's key to making all of these arguments work. So of course, Weierstrass preparation says that if you have a sufficiently regular, some kind of regularity, which you have to be clear about what that means, about your polynomial, about your power series, then you can divide up the domain into sets on which locally the power series can be written as a unit times a polynomial. So a unit in all of the variables times a polynomial in the last variable. And you can do that rearrangement of what is the last in order to satisfy your regularity condition. But so that's a strong property of your, it's kind of a closure property on this collection of functions that you've chosen to work with. But it's the key, and of course it's satisfied by if we just take all of the polynomials, all the power series. So we have a chance of being able to satisfy it. But then that's where that gets, that's what you need in order to make all this work. You also need a strong Noetherian property so to make other pieces work. And then you've taken this very formal structure. I took an arbitrary ring A and I took formal power series. And so we need to be able to think of them as functions. So I have to have a collection of homomorphisms from my ring to a function which is valued in the valuation ring. So a map to the valuation ring from the valuation ring cross the maximal ideal. So that just says, okay, if you've got a point and a value of X in the valuation ring and a value of rho in the maximal ideal, you can take your power series and evaluate it as an element of the valuation ring. So we have a way of doing evaluation. So all of that's very formal, but we have a natural example, which is the, just take from the beginning my ring A just to be the valuation ring of the field that we're looking at. Take each set A, M, N to be all of the convergent power series in the X variables and all power series in the row variables. And then we can just take our, looks like this kind of went off the bottom of the page here. Let me see, just turn that off. There we go. Then the, just taking the homomorphism to be just evaluate, and I've chosen in such a way that my power series do actually converge, then this is kind of the basic example of such a separated analytic A structure. And then, so given the separated analytic A structure, we can add function symbols for all of the elements of all this A, and we can and so work in that language, and we know how to interpret these function symbols in our standard model because we have the functions which we added, the homomorphism sigma, which allow us to do that. So then in this paper, Fields with Analytic Structure, Raff and Leonard proved that the theory of an algebraically closed valued field has quantifier elimination and is C minimal. Okay, so that's really nice. It gives us an axiomatic way to choose the sets of functions that we're going to look at. It gives us a really nice theorem, but it does not do the ordered valued field case, which is still what I want to look at. So one way you can add the ordering is by working with the over-convergent series. And this is something that Leonard Lipschitz and Zach Robinson did in an earlier paper. So it's not exactly the fields with the analytic structure set up because they hadn't developed that yet. So I'm just being a little bit paraphrasing here by setting it into that context. But if we do so, we can set it up and put it in that context. Take the collection of over-convergent series. So that is the one, remember, the ones that converge on a ball which strictly contains the valuation ring. And then take our functions to be those which take the value of the function provided x is in the unit box, so -1, 1 to the n. This set will be a small subset of the open ball radius epsilon. So definitely within the domain of convergence of the power series. Work in the language of ordered fields, and then again, do the usual thing, add the symbols for the collection of series that we're looking at. And then we get quantifier elimination and O minimality. So that's a slightly odd statement because we have, we're looking in the language of ordered fields with function symbols for functions which are over convergent. So convergent on in the sense of the valuation, but we're looking at those functions on an order definable set. So we have a very curious mixture of the valuation and the ordering here. And we do indeed get O minimality. I mean, notice that the valuation is not part of the language. I didn't put that in. So that's a nice theorem, but it's not the theorem that I want because I want to talk about functions which are valuation definable and have their domain given by a valuation condition and not by an order condition. So okay. So what Pablo and I did was to take a collection of function that forms a separated analytic structure, and then to take the functions to be evaluated on the kind of in the way that they're set up to be evaluated. So for the x variables in the valuation ring and the rho variables in the maximal ideal, and then to look at it in a language for ordered valued fields. So my analytic functions are defined by the valuation, and the convergence is defined the conditions on the valuation, and their domain is valuation definable. But then I also am working in the situation in which I have an ordering. And then we can prove that we do indeed get quantifier elimination. In the theory of a real closed convexly valued field, we get quantifier elimination and weak O minimality. So that's the expected result, but it's the result that we want in order to try to push forward. So I'm just looking at the names of everybody who's here and looking at the audience who I can't see, so I don't know who's there. I put together just an outline of the proof, but in a certain amount of detail. So this is all going to be a little bit technical, but well, I think everybody's going to be up for it. Okay, so this proof goes as all of these proofs go. So it's a standard argument. You just have to follow through. You have to be careful of the technicalities. So I'll just kind of outline the way all of these go. And if you go back and are reading some of those old papers, then you can see that that's what was going on there. So the first step, standard reductions, we only need to eliminate one existential quantifier. So given a quantifier-free formula, 5 x and lambda, y and rho, where x and lambda are going to be we're thinking of them as tuples, and y and rho we're thinking of as single variables. Then we want to show that there's a quantifier-free formula so that the existential formula quantifying out the variables y and rho is equivalent to a formula without that existential quantifier. And standard trick, at the expense of introducing extra x and lambda variables, we can assume that the inverse function is only applied to terms not involving y and rho. So that makes things, functions that are going to come up, less complicated. And then we think about, okay, so now what can we be saying in our formula? And to say, okay, well, there's the bit which just involves x and lambda, that's fine. And then what can we be saying about the variables y and rho? Well, we can, given that in our language we have equality, we have an ordering relation, and we have the valuation relation, which we put in as div. So we put in as valuation of something is less than some valuation of something else. The things that we can say are equations. We can say that something is positive. We can say that something has valuation 0, or we can say a valuation condition between two terms. And the functions, we have functions. These are not function symbols; these are functions given by terms. Expressions given by terms. But what we can do is to break our domain, the domain into definable sets on which each function can be written as a function involving the variables x and lambda and a function involving the variables y and rho. And we do this in such a way that we have some regularity on the function g so that we can then apply Weierstrass division. And that's the key point here is to be able to apply Weierstrass division at this point. That's locally, of course. So we have to think about what the definitions of those local sets are, where that can happen. All right, and then, as I said, using regularity, induction, and great care, we write G, we use Weierstrass preparation to write G as a unit times a polynomial in either y or rho. And then these conditions that I said about being equal to 0 or being positive or valuation condition as conditions in either the y or the rho variable become algebraic conditions because I have a polynomial there instead. And then we can apply algebraic quantifier elimination, and then we eliminate the variable, that quantifier. And then to prove weak O minimality, we again do this kind of the similar calculation to see that we're reduced to studying atomic formulas where we say that a term is equal to 0, or a valuation condition on two terms, or that a term is positive. And I've now reduced to S and T being terms in one variable. And I realize I should have a row in those as well. So we just sort of chosen whether it's row X or rho is the key variable at that point. And then again, we need to understand what are the definable functions given by a term in one variable. And there's a further theorem in the paper of Kluckers and Lipschitz to say that if we work in the algebraic closure, then there's a definable partition so that a term in one variable can be written as the product of a rational function and a unit or a strong unit. And this definable partition, which is definable in the algebraic closure, turns out also to be definable in the real field. And so that we can indeed write our term here as a rational function times a unit. And then the unit will either have valuation 0, and so it's irrelevant to this kind of condition, or the unit will have constant sign, and so it's irrelevant to this condition. And so again, my conditions become algebraic. Well, they're given by a rational function, and then we can use linearity. We can use the fact that we're in an algebraically closed field or a real closed field to see that those are actually linear conditions. And so that gives us the weak O minimality that we wanted to have. So that's kind of in very broad terms how you make this work. And that's all I wanted to say. Thank you.